Hey everyone, welcome back to Statistics. Here's Jonathan, and today we'll start lecture 3, conditional probability. So what is conditional probability? Suppose that you have two events, A and B, such that the probability of B is positive. We denote the probability of A given B, the probability of A given that B has occurred. Okay, so now I'm going to ask what is the probability of A given that B has occurred. So we can think about B as information, and the question would be, given this information, what is the probability of A? So here's the definition. How exactly we compute conditional probability? So the definition says that if we want to compute the probability of A given B, what we need to do is to take the probability of the intersection over the probability of the information. Assuming, of course, that the probability of B is positive, otherwise it's not well defined. Now I want to explain what is the intuition behind this definition. Okay, so let's use a Venn diagram. And let's draw those two circles that represent the events, A and B. And here is the sample space, omega. Now someone is telling you that B occurred. Therefore, the only thing that now is relevant is what happens in B. Okay, now the question is, given that B occurred, what is the probability of A? The only part in B where you can find some elements of A is here, the intersection itself. So here's the intersection. And now in order to compute the probability of A given B, that's exactly the same as asking what is the fraction of the intersection over the probability of B. One more formula you should know is what we call the product rule. So let's see. The definition of the conditional probability A given B, we saw that that's the intersection over the information. Now from here we can write the probability of the intersection by using algebra as the probability of A given B times the probability of B. And that's exactly the product rule. We'll see in a few minutes how exactly we use the conditional probability and the product rule. So here's an example. Suppose that we roll 2 die. And we denote A as the sum of the outcomes is at least 11. Great, let's write A explicitly. A, the elements are 5 and 6, 6 and 5, and 6 and 6. Now, if I ask you what is the probability of A, you know that because it's a symmetric sample space, that's the cardinality of A over the cardinality of omega. How many elements do we have in A? 3. How many elements do we have in omega? 36. Therefore, the probability is 1 over 12. Great. Now, let's denote B, another event, as the first outcome is 6. Now, I want to ask you, what is the probability of A given that B occurred, meaning that the first outcome is 6? Okay, so we use the definition. That's the probability of the intersection over the probability of the information. Great. It's a symmetric sample space. Therefore, the numerator will be the cardinality of A and B over the cardinality of omega. All of that over the cardinality of B over the cardinality of omega. Great. Those two are cancelled, and then it becomes the cardinality of the intersection over the cardinality of B. So now we need to understand how many elements do we have in the intersection, how many elements do we have in B. Let's start by the cardinality of B. So let's write B explicitly. B again, that's the first outcome is 6. Okay, first outcome is 6. That means that the first one can be 6 and then 1, 6 or 2, and so on until 6 and 6. So how many elements do we have in B? That's exactly the cardinality of B, exactly 6. Okay, so let's write it, 6. Now we need to find the intersection. So asking what is the intersection of A and B, it's exactly the same as asking what are the elements that belongs to A and also to B. So here are the elements. We have 6 and 5 and 6 and 6. There are only 2 elements. Therefore, that becomes 2 over 6, 1 over 3. So let's see. We started by asking the question, what is the probability of A? Then we got 1 over 12. Now, if I ask you, what is the probability of A given the information B? That becomes 1 over 3. So we updated the probability of A given the information. Let's continue with example 2. In class, there are 80 students. The lecturer prepared 2 exams, 50 copies of the first exam, 30 copies of the second exam. The exams are mixed. What is the probability that the first 2 students get the same exam? Great. So how do we solve those types of questions? So here's the answer. First, we denote A to be the first student received the first exam. B, the second student received the first exam. Great. So now that we denoted A and B, we defined them. Now we need to understand what is exactly the question. So how we can write this question in terms of probability. Okay. So we need to understand what we mean by the first 2 students get the same exam. So there are 2 possibilities. One option is that both students get the first exam, meaning A and B. Another option, because we have only 2 different exams, is that the first student get the second exam, meaning not A, and also the second students get the second exam. So that's exactly, these events mean exactly that the 2 students get the same exam. One more time, why? Here, A and B means that the first student and the second student get the first exam. Not A and not B means that the first student get the second exam, and the second student get also the second exam. And that's exactly equivalent to saying that both students get the same exam. Great. Now, if you draw a Venn diagram and you try to draw this event, so you'll see, let's do it, you'll see that both events are disjointed. let's see, that's A and that's B. So what is A intersection B? A intersection B, that's exactly the middle point. Now, what is not A and not? If you use the model laws, you can write not A and not B as A union B and the complement of that. That means that if you draw it in the Venn diagram, that becomes the red area. So from here, you can see that both of them are disjointed. Therefore, according to axiom 3, you can separate it into two. So the probability of A and B plus the probability of the complement of A and the complement of B. Now, we can use the product rule and write the first intersection as the probability of B given A times the probability of A. Exactly the same for the second one, the probability of the complement of B given the complement of A times the probability of the complement of A. Again, so we use twice the product rule, one time for the intersection of A and B and another time for the intersection of complement of A and the complement of B. Great, now we need to figure out what those probabilities are. Okay, so let's start by the probability of A. So we know that there are 80 exams in total. 50 belongs to the first copy, so 50 of the first, and we have 30 rows of the second one. Okay, so if I ask you what is the probability of A, that means what is the probability to get the first exam? So 50 over 80. Great. What about the complement of A? So you can do the same, but if you know that the probability of A is 50 over 80, so the probability of the complement needs to be 30 over 80. Okay, great. Now, we need to understand what is the probability of B given A. So now A represents that the first student get the first exam. So in case that the first one truly get the first exam, so instead of 50 first exams, that becomes 49 out of 79. Okay, so now if I ask you, what is the probability of B given A? That's equivalent to ask you, the first student got the first exam. What is the probability now that the second will get also the first exam? And that probability is exactly 49 over 79. Now let's do the same for the probability of the complement of B given the complement of A. Okay, now let's do it again. So in total we have 80 exams, and we have 50 of the first one. Okay, someone is telling you that the first students got the second exam. So that means that we have 29 copies of the second exams out of now 79, because the first one already received the second exam. So now, what is the probability, after updating the information, what is the probability that the second one will receive the second exam? That's exactly 29 over 79. And that's all. So that's how we use, in general, the product rule. Okay, so now I'd like to continue with conditional probability and talk about the complement. So I want to prove that the complement of A given B is the complement of A given B. Oh, another way to write it is that the probability of A given B, that's 1 minus the probability of the complement of A given B. By the way, another way to write it is that the probability of A given B plus the probability of the complement of A given B is 1. Let's prove that. Okay, so here's the proof. So what is the probability of A given B? If we use the definition, that's the probability of A and B over the probability of B. And what is the probability of the complement of A given B? That's the probability of the complement of A and B, again, by using the definition, over the probability of B. Okay, so they have exactly the same denominator, and therefore we can write it as the probability of A and B plus the probability of the complement of A and B, all of that over the probability of B. Now let's draw a Venn diagram. So here is A, here is B. Now let's see. The probability of A and B, that's exactly the middle part. The probability of B and not A, that's exactly, we already saw that, that's exactly that part. So if we sum the blue area with the black area, we'll get what? Exactly the probability of B. So the probability of B over the probability of B, that's exactly 1. And that's all. Let's solve this exercise. I want you to show that the probability of A union B given A and B equals to, I hope that you know that, it's 1. Why? So I'll explain the intuition, but first, let's see how we prove that. So let's see why it's true. So here's the proof. So what is the probability of A union B given A and B? According to the definition of conditional probability, that's A union B, all of that, and the intersection A and B. All of that given the probability of the intersection. Now, if we draw the Venn diagram, again, it's very useful to use the Venn diagram. Okay, here's the Venn diagram. So I want to take the intersection of A union B and A and B. So let's draw A union B. A union B, that's all the circles, A and B. What is A and B? That's exactly the intersection. And if we take the intersection of the blue color with the red color, that becomes the red color, the intersection itself. So we have the probability of intersection over the probability of the intersection, and that needs to be 1. Now, that's the proof. Let's try to understand what is the intuition. If someone is telling you that A and B occurred, of course, A union B needs to occur. Why? Because A and B is part of A union B. That's a subset of A union B. And that's the intuition. Why? We need to get 1. Let's do a bigger example. Suppose that we have an investor that buys 2 stocks. We already saw a similar example. With probability 0.7, the first will rise. With probability 0.6, the second will rise. And with probability 0.1, the first and the second won't rise. What is the probability that both stocks will rise? So again, we need to denote A, B, and C. So let's denote A to be the first will rise. Let's denote B as the second will rise. So when we denote it like that, so now we can write explicitly our probability. So the probability of A, that's 0.7. The probability of B, that's 0.6. And the probability that the first and the second won't rise, that's the probability of not A and not B, and that's exactly 0.1. Now, trying to compute what is the probability that both stocks will rise, that means that we want to compute the probability that A and B occurred. Okay, so what is the probability of A and B? So we can use what? We can use first the De Morgan law. Why? We know that 0.1 equals the probability of the complement of A and the complement of B. But using the De Morgan law, we can write this as the probability of A union B and the complement of all of them. That's exactly 1 minus the probability of A union B. So from here we get that 0.1 equals to 1 minus the probability of A union B, meaning that the probability of A union B is 0.9. Please remember, that's not what we need to compute here. We need to compute the intersection. But in order to get the intersection, we need to compute the union first. Okay, next, I can use the formula that we already saw in class that says that the probability of the intersection equals to the probability of A plus the probability of B minus the probability of the union. So we have everything here. In order to solve the question, we have the probability of A, 0.7. We have the probability of B, 0.6, minus 0.9. And in the end, we'll get 0.4. So that's how we solve A. Let's continue with section B. It's not that the first stock rises. What is the probability that the second stock will rise? Okay, so here's the information from the previous section, and we also added those two. Now, we are asked to compute the probability of something given, something else. Here, please remember that you'll need to write the information that is given. Here, you'll need to write the event that we want to compute the probability of. Okay, so what is the information here is that the first stock rise. First stock rise means that A occurred. Now, we are asked what is the probability that the second will rise. So we use the definition of conditional probability. So that's the probability of the intersection over the probability of the information. So we already have here the probability of the intersection. Please remember that the probability of A and B, that's exactly the same as the probability of B and A. So that's 0.4 over the probability of A, 0.7. So it's 4 over 7. Let's continue with C. It's known that the second didn't rise. What is the probability that the first won't rise? So we need to write explicitly this probability. So the information is that the second one didn't rise. What is the probability that the first one won't rise? Okay, now we need to use again the conditional probability. So that equals to what? To the probability of the complement of A and the complement of B over the probability of the information, meaning the complement of B. So the probability of the complement of A and the complement of B is already given in the question. That's 0.1 over the probability of the complement of B. So if we know the probability of B, we also know the probability of the complement. That's 1 minus. So that's 0.4. So from here we get 1 over 4. Now I'd like to talk about independent events. So if the probability of A given B equals to the probability of A, that means that the probability of A occurring is not affected by the occurrence of B. So let's write it. Then the probability of A occurring is not affected by the occurrence of B. In this case, we say that A and B are independent. So another way to say that is that if you compute the probability of A given B, and you don't need to update A, because in the end that equals to the probability of A, that means that A and B are independent. So here's the definition. A is independent of B if and only if the probability of A given B equals to the probability of A. By the way, notice that we can prove that, well, we won't do it, that if A is independent of B, then also B is independent of A. Okay, by the way, there are equivalent definitions to the idea of independent events, and I'd like to write them. We are going to use a few of them. Okay, so equivalent definitions. So we already saw that the first definition that says that A and B are independent if and only if the probability of A given B equals to the probability of A. Another definition that we mentioned is that it's exactly the same as saying that the probability of B given A is equals to the probability of B, because we said that if A is independent of B, then B is independent of A, and also the inverse. Okay? So those are two equivalent definitions. Now let's see the third one. That's a new one. So if the probability of the intersection equals to the product of the probability of A times the probability of B, then from here you can say that A and B are independent. Why? So here's the reason. Because if A and B are independent, let's write independent I and B, okay, instead of writing each time independent. So if A and B are independent, so the probability of A given B, according to the definition, that's the probability of A and B over the probability of B. That's the conditional definition. Great. But if A and B are independent, that means that the probability of A given B, that's exactly the probability of A. So from here we can write that the probability of A given B, that's exactly the probability of A. That equals to the probability of the intersection over the probability of B. Now by using algebra, we can multiply by the probability of B. And from here we get that the probability of the intersection equals to the probability of A times the probability of B. So here that's exactly why it's an equivalent definition to the idea of independent events. Now let's continue with an example. Suppose that we have a standard card deck with 52 cards, no jokers. And we take out one card. A is defined as a face card. So what do I mean by face card? Well, jacks, queens, or kings. Great, now let's define B. B is diamond card. Great. Now here's the question. Are A and B independent? So in order to answer this question, we're going to use one of the definitions that we saw. Let's use the third definition. So let me remind you, the third definition says that A and B are independent if and only if, by the way, we can write if and only if as by using this symbol, the probability of A and B equals to the product of A times the probability of B. What we're going to do now is to compute the probability of A, the probability of B, the probability of an intersection. And if the probability of the intersection equals to the product, we'll say that A and B are independent. Otherwise, they are dependent. Okay, so let's start. Let's compute the probability of A. Now, in general, in a card deck, we have 4 types of cards. We have the clubs, the diamonds, the hearts, and the spades. So we have 4 types. So maybe I needed to mention it before that, but anyway, I mention it now. So 4 types. And now I want to compute the probability of A. We have 3 face cards and 4 types of each of those. That means that we have, in general, 12 face cards out of 52. That's exactly 3 over 13. Now let's compute the probability of B. How many diamond cards do we have? Exactly 13 cards. So 13 over 52. That's exactly 1 over 4. Now the only thing now that we need to do is to compute the probability of the intersection. So what do we mean by intersection? A and B. A and B means that we have the elements in A and B are the diamond, jack, diamond queen, and diamond king. And we have only three options. So if I ask you what is the probability of A and B, exactly the cardinality of A and B over the cardinality of the sample space. So we know that the cardinality of the intersection, that's 3. Over the cardinality of sample space, we have 52 cards, so 52. Okay, so we have the probability of the intersection, we have the probability of A and the probability of B. Let's see what do we get from here. So we know that the probability of the intersection, that's exactly 3 over 52. And we know that the probability of A times the probability of B, that's exactly 3 over 13 times 1 over 4. And the question is, do we have equality here? Is the probability of the intersection equal to the product? So you can check, you can use your calculator, and you'll get that the answer is yes. Therefore, the conclusion is that A and B are independent. That's all. Now, before we finish this example, let me try to explain what this result means in the end. Okay, so here, the example, we ask, are A and B independent? Meaning that suppose that someone is telling you that the card that you chose is a diamond card. Will it affect the probability that we get a face card? And the answer is no. Why? Because we proved that they are independent. So now that we know they are independent, knowing that the card you chose, you took out is a diamond card, doesn't change anything. It won't affect the probability that it's a face card. Now I'd like to talk about 2 different properties. Let's start by the first one. Suppose that we have 2 events that are disjoint. Then they must be dependent. Why? So we won't prove that, but I'd like to show you the intuition why it's true. Okay, so let's draw A and B. Here's the sample space. Okay? Now let's assume that A and B, the probability are positive. It's not an empty set. Okay. Now, suppose that I ask you, what is the probability of A given B? Now, let's think about it. If B, that means the information, so it means that B occurred. It means that I'm here somewhere. But now I'm asking you, suppose that B occurred. What is the probability that A occurred? So it means that, in other words, assuming that I'm here, what is the probability that I'm here? So, of course, that needs to be 0. But if it's 0, we say, a few minutes ago, we said that A and B are independent if and only if the probability of A given B equals to the probability of A. Now, if that equals to 0, and the probability of A is positive, of course, here we get an inequality. And therefore, from here we get that the probability of A given B doesn't equal to the probability of A, meaning that they are dependent. So again, the idea is that if I ask you what is the probability of A given B, B occurred. I can never be an A, okay? And therefore, this probability is 0, and the probability of A is positive, and therefore, the probability of A given B is the probability of A. And from here, I conclude that A and B are dependent. Okay, next property says that if A is a subset of B and B isn't the sample space, then A and B are dependent. Again, we won't prove that, but I can show you intuitively why it's true. So A is a subset of B, meaning that A is here and B is here. That's the sample space. Now, if A is a subset of B, and I ask you what is the probability of B given A, okay? Now we can use the definition of conditional probability. So it's B and A over the probability of the information, meaning the probability of A. So the probability of B and A, that's exactly A. So what do we get? Probability of A over the probability of A, that's 1. Now, folks, that cannot be the probability of B. Why? Because we know that B isn't the sample space. The only option that probability of B is 1 is only if B is the sample space. Okay, so again, the only way that the probability of B is 1, it's only if B is the sample space according to axiom 2. So we know that, in the end, from the probability of B given A, we get 1. But it cannot be the probability of B. Therefore, from here we get that the probability of B given A, let's know the probability of B. And from here we get that B and A are independent. That's all. Okay, there are 2 more properties. Let's continue. Property number 3. If A and B are independent, then A and the complement of B are independent. 2. Complement of A and B are also independent. 3. Not A, not B are independent. Okay, so you can use that in order to solve different questions. We'll see later on, but for now, please remember that if A and B are independent, also those 3 are true. By the way, vice versa also. So I mean, if A and the complement of B are independent, so do A and B, and so do the complement of A and B, and even the complement of A and complement of B, all of them are independent. Okay, so we won't prove that, and we won't see the intuition behind it, okay, because there's not really intuition. The only way to understand it is to prove that, and we'll skip it for now. Okay, so let's talk about the last one. For all A event in omega, for any event in omega, A, such that A isn't omega, A is independent of the empty set and the sample space. Okay, so let's try to show why A is independent of the sample set. We can do the same for the empty set. Okay, so let's see. So we want to show that the probability of A given the sample space equals to the probability of A. That if someone is telling you that the sample space is pure, it doesn't affect the probability of A. Okay, now by the way, that's exactly what the definition means. I mean, the independent definition means that if someone is telling you some information, it doesn't affect the probability of the event that you try to compute the probability of. Okay, so let's see. So from here, we can use the conditional definition. We get that the probability of A given the sample space, that's exactly A and the sample space over the probability of the sample space. That equals to what? So A and the sample space intersection, that's exactly the probability of A. We already saw that, and you can draw also the event diagram, and you'll see that that's exactly what we get. And that's over the probability of the sample space. So the probability of the sample space, according to axiom 2, that's exactly 1. So we get from here that equals to the probability of A. So from here we get that the probability of A given the sample space equals the probability of A. That means that the probability of A given the sample space, that's exactly the probability of A, and that means that A and the sample space are independent. Okay, so that's one way to show that. I mean, that's the proof. Now, let's suppose that someone wants to understand the intuition. Let's see why, from the intuition itself, we can truly understand that they must be independent. Now, let's draw a Venn diagram. So here's A, here is the sample space. Now, suppose that someone is telling you that the sample space is pure. What is the probability of A given that? So that's exactly the probability of A. In the end, you need to remember that you know that you're doing the experiment. So, for example, think about it. If you roll a die, and I ask you what is the probability to get 1, given that you can get 1, 2, 3, 4, 5, or 6. Okay, that's exactly the probability to get 1. Okay, so given the information that the sample space is pure, it doesn't affect any event, and therefore they must be independent. So that's the intuition, and that ends lecture 3. See you on the next lecture.